Someone is sitting at a desk, waiting. On the screen, a program is typing away, a program that is supposed to be faster than a human, and the human beside it does nothing. They read along, they watch, they hope the thing does not head off in the wrong direction. This is exactly the moment we are concerned with here. What is actually the work of a developer, while a machine is programming for them? The simple answer up front: it is not the watching.
A quick framing so everyone can follow. An AI coding agent is a program you give a task to in plain language, build this feature, fix this bug, and which then independently writes and changes code. Tools of this kind are called, for instance, Claude Code, Cursor, or Aider. What is new is not that such an agent writes code. What is new is the question of what the human does when they no longer type the code themselves.
One person who has chewed this question over in public is Steve Yeg, a veteran. This man has been programming for around 40 years. He was at Amazon, at Google, most recently at SourceGraph. And he, of all people, describes the problem with full candor. With a single agent, he says, you run into a wall. The context gets lost. You cannot parallelize. And in the end, you spend as much time babysitting the AI as you would have needed to write the code yourself.
And by babysitting, he means it literally. He describes how, at a party at the weekend or in bed at night, you keep checking your phone. Is my agent still on track, or has it gone off the rails? That is the first trap. It comes from a familiar habit. One ticket, I write the code, I read it through. This pattern gets carried over one-to-one onto the agent, and then you sit waiting beside it. Throughput hangs on a single agent, and you yourself are the bottleneck.
But Yega had a different idea early on. Already in March 2025, he predicted what was coming.
Every developer will run many agents in parallel at once, each on a different task. That is how he put it. One fixes a bug, the next builds a feature, the third writes documentation. That is the first and most important reframing of one's own role, not waiting idly for one agent, but directing several at the same time. The waiting time does not disappear because the single agent gets faster. It disappears because you fill it with other agents.
Sounds simple, but it isn't, because now comes the moment where most people run into the wall, and Yega is no exception.
If you put two agents into the same project directory at the same time, chaos ensues. One changes a file, the other changes the same file. They overwrite each other, and in the end, nothing fits together anymore. More agents then means not more progress, but more confusion.
Why not simply solve that by giving each agent its own workspace?
That is exactly the solution, and it has a name: Git worktrees. A worktree is, put simply, a separate, distinct working copy of the same project. Each agent gets its own folder, its own copy. It can tinker away in there without getting in its neighbor's way. The command for this is simply git worktree add with a path and a branch name. Then you start one agent per worktree. That way, 20 agents work side by side without shooting each other's files to pieces. That is the third building block: isolated workspaces.
But there remains a question over which Yegeg gnashed his teeth for months. For 20 agents to work on 20 things, someone must first cut the work cleanly into 20 independent pieces. And it was right here that he built something big, something very big.
For agents to be able to work independently, you have to break the work down into subtasks that do not block one another, each with a clear acceptance criterion, that is, an unambiguous condition by which you recognize that this task is really done. Feels done is not enough. The tests pass and function X returns Y is enough. Without this clean cut, the agents grab into each other's work.
Yega's answer to this was a vast orchestration system. For 6 weeks he built 350,000 lines of code, a whole apparatus that was supposed to coordinate the agents. And this apparatus failed, from its own architectural mistakes, collapsing in on itself. 6 weeks, 1/3 of a million lines, for the bin.
And then comes the punchline, and it is almost disappointingly simple.
The actual solution took 15 minutes.
15 minutes. Yege realized the agents need no huge control apparatus at all and no endless plan documents in text form. They need a simple, structured, queryable list of tasks, a task graph stating which task exists, what it requires, and whether it is done. From this came a small tool called beads. It stores each task as an appended line in a file that travels along with the version control. A new line added, never an existing one overwritten. As a result, 20 agents can write to it at the same time without conflict.
That is the joke of the whole story. The big, expensive system was not the solution. The big system was the detour. The solution was small, almost banal, and that is exactly why it works. He calls the problem behind it, by the way, the 51st dates problem. Agents have no memory between two sessions. Every time they start from zero. The small task list is their memory.
And with that, only the fourth building block is missing, the ongoing directing. Agents go astray. One spends 40 minutes turning the crank on the wrong problem without anyone noticing. That is why orchestrating needs an observing layer. It watches the running agents, nudges the stalled ones, and flags the ones that have drifted off course. In Yege's later published system, Gastown, a dedicated watcher role takes this on. But the principle needs no big system. Observe, unblock, re-aim.
At the end of this path stands a sentence that Yege phrases like this.
I have tamed them so well that you can keep 20 to 30 running productively at once.
From a waiting babysitter to 30 parallel agents. That is the leap.
And the core for one's own practice is this. The productive work while the agents are programming is not watching, but orchestrating. Break work down into independent pieces with clear done conditions. Give each piece to an agent in its own work tree. Observe the running agents. Unblock them. Re-aim them. This has a hard limit. It only works if the decomposition is thought through from the start. Whoever first sets 20 agents loose and then looks at what comes out does not get throughput, but chaos. Orchestrating does not fix bad habits. It amplifies them. The gain is that human attention is freed for where it is really needed.
With which a second question remains open, one that is at least as important. When 30 agents spit out code in parallel, no one can read it line by line anymore. How does one then trust this code at all? That is the other half of the same loop, the checking, and the next part of this series is devoted to it. For distributing is only half the work. The other half is being able to trust the result.